Have you ever built a machine learning model that seems like an absolute genius during training, but then it just completely bombs when it sees new data? It's a super common problem. But what if I told you the solution is to hire a personal trainer for your model? Well, that's pretty much exactly what regularization is.
All right, let's get into it. Here's our workout plan. First, we'll diagnose the problem we're trying to fix. It's called overfitting. Then, we're going to meet our model's personal trainer, regularization. We'll check out its two main training styles, see the cool science behind why they work, look at a real-world model that went from failing to fit, and finally, figure out how you can choose the right training plan.
So first things first, let's really get a handle on the problem. Think of it like a model that's an absolute genius in practice runs, but completely fails the final exam.
And that really is the heart of it, isn't it? A model that just memorizes the answers to the training data hasn't really learned anything. All it's done is create a perfect cheat sheet that's totally useless for any new questions it hasn't seen before.
This analogy is just perfect. The model has learned all the noise, all the little quirks and random details in the training data, but it hasn't grasped the bigger picture. So when it faces that actual exam, new, unseen data, it just has no idea what to do.
So on one end of the spectrum, you can have a model that's underfitting. I want you to just picture a simple, straight line trying to capture a bunch of data points that form a curve. It's just too simple, right? It misses the real trend entirely. So it's not accurate on the training data, and it's not going to be accurate on new data either.
And then you've got the total opposite extreme, this crazy zigzag line. That's our overfit model. Its equation is super complex, which lets it perfectly nail every single data point it was trained on. But just look at it. It's obviously not capturing the real underlying pattern. This thing is going to be terrible at predicting any new points.
And right here, this is the goal. This is our just right model. It's complex enough to see the general curve in the data, but it's simple enough that it ignores all that random noise. This is the model that can actually generalize and make good predictions.
So, to boil it all down, overfitting is basically a failure to generalize. The model memorized the answers instead of actually learning the method to find them.
So, how do we force our model to actually learn the method instead of just memorizing? Well, we bring in a trainer.
And that trainer's name is regularization. It's a whole set of techniques that are designed to stop the model from getting way too complex and over-specialized. It's the tough love that makes sure our model stays lean, mean, and effective.
Okay, so how does this trainer actually work its magic? Well, a model learns by tweaking thousands of little internal knobs. We call them weights. Normally, its only goal is to get the answer right. But regularization adds a second rule: keep those weights small. It adds a penalty to the model's score for every large, complex weight it tries to use. This forces the model to find the simplest possible way to solve the problem, not the most complicated one.
Now, this trainer isn't a one-trick pony. It has two very different training philosophies, and they're known as L1 and L2 regularization.
You can think of L1, which is also called lasso, as a specialist trainer. He looks at all the features and says, these two are important, we're going to work on them. The rest, forget them. It can actually make the importance of some features go to zero. Then you have L2, or Ridge. He's more of a holistic trainer. He says, okay, we're going to work out all the muscles, making sure they all chip in, but no single one gets way too big and dominant.
So how do these two styles actually work under the hood? What's so cool is that we can literally visualize the mathematical difference between them. This isn't just some abstract idea, it's actual geometry.
Yeah, why is that? Why does one trainer just completely get rid of features, while the other one just kind of tones them down? Well, the answer comes down to the literal shape of their penalty.
When we graph the limits these penalties put on the model's weights, we see two totally different shapes. The L1 penalty gives us a diamond, and the L2 penalty gives us a circle.
And this is where it all clicks. Imagine the center of a target is the point of perfect accuracy on your training data. The model wants to get as close to that center as possible. But the penalty function says, nope, you have to stay inside this shape, either the diamond or the circle. For the L1 diamond, the easiest way to get close to the center is often to hit one of those sharp corners. And here's the key. Those corners lie on the axes. Hitting a corner means the value for the other axis becomes 0, which effectively eliminates that feature from the model. With the smooth L2 circle, there are no corners, so the model gets close to an axis, but it never lands perfectly on it. The weights get really, really small, but they never quite disappear.
Okay, enough with the theory. Let's see what happens when we use this on a real problem. We're going to use a data set of housing prices from Melbourne, Australia.
So without any regularization, our first model gets a score of 68% on the training data. And you might think, hey, 68%, that's not too bad. The model seems to have learned something.
But then, here comes the moment of truth. We show the model new data it's never seen before, and the score just plummets to a dismal 14%. That is a textbook classic case of overfitting. It memorized the training houses, but learned nothing about the actual housing market.
So now we bring in the trainer. After applying regularization, the score on that same unseen test data skyrockets to about 67%. I mean, just look at that difference. The model was forced to generalize, and its performance on new, strange data became almost as good as its performance on the data it already knew. It's a huge win.
So, it's pretty clear that regularization works. The final question is, which trainer should you hire for which job? L1 or L2?
This chart is basically your cheat sheet. If you think most of your features are probably useful and they all contribute a little bit, you should use L2 Ridge. It'll balance them all out. But if you suspect that a lot of your features are just noise and only a few really matter, then you want L1 Lasso. It'll do automatic feature selection for you, giving you a much simpler, more focused model.
And that really leaves us with a final thought. Regularization isn't just some technical knob you turn. It's a strategic decision. It forces you to think about what you actually want your model to pay attention to and what you want it to ignore, transforming it from a lazy memorizer into a lean, effective, and truly intelligent machine.